In this video, we're going to show you how to do hypothesis tests involving a population proportion. We'll do an example of a right tail test, a left tail test, and a two tail test. And basically the way we'll determine whether or not to accept or reject a null hypothesis is simply using p-values. Remember, if the p-value is less than or equal to alpha, you reject the null hypothesis. If the p-value is greater than alpha, you accept the null hypothesis. Okay, so we'll go through three problems here, and you'll see in each of the worksheets for our examples here, we've got right-tailed test, which means the alternative will be a proportion is greater than some number. We have a left-tailed test. The alternative is the proportion is less than some number, or a two-tailed test, where the proportion is not equal to the proportion in the null hypothesis. And then we've got the formulas for the p-values right here. You don't have to do a single thing. Okay, and we'll sort of explain how those formulas make sense as we do our examples here. So basically all you'll have to do in hypothesis testing problems involving a population proportion is basically put up how many trials you had, how many successes, and what was the hypothesized value of the population proportion, the null hypothesis, and the p-values pop right out, pick out the one that corresponds to whether or not you have a right tail test, a left tail test, or a two tail test. So let's go through these three examples. Player makes 300 of 400 free throws, okay, before they were 70% foul shooter and they hired, let's say, a new coach. So are they a better foul shooter after they hired the new coach? 300 out of 400 is 75%, so they did better. The question is, did they do significantly better? We'll use alpha being 0.05. Okay, so the null hypothesis is that their chance of making a free throw after the change, which we call P, would be less than or equal to 0.70. They weren't any better. The alternative hypothesis is their chance of making a free throw after hiring the new coach is greater than 0.70. So all we do is put that information over here. P0 is 0.70. The number of successes, a success is making a free throw, is 300. Number of trials is 400. Okay, and it's a right tail test because you have a greater than sign here. The p-value is 0.016. That's less than or equal to 0.05. We reject the null hypothesis. Now, how did I get that p-value? I just simply came up with, if you were a 70% foul shooter, what's the chance you'd make at least 300 out of 400? And the answer is very small, 0.016. So we reject the hypothesis that you're a 70% foul shooter and the new coach helped you. Okay, now let's do another example. Okay, we want to know if a coin is fair. We tossed that coin 400 times and 217 times out of 400 it came up heads. That's about 54% of the time. Now the null hypothesis involves the chance that the coin comes up heads. That chance would be 0.5 in the null hypothesis. The alternative, the coin not being fair, simply means that basically the probability of the coin coming up heads is not 0.5. Okay, so that's a two-tail test. So we'd use the p-value down here. So basically p0 is 0.5 because we're assuming a fair coin in the null hypothesis. The number of successes is 217 out of 400. And then this probability, sort of, you have to double the probability from the smaller tail. Okay, I don't know exactly which here would be the smaller tail here. Okay, but basically you get a p-value of 0.0988. So basically for alpha equal 0.05, we would accept the null hypothesis. That's not enough evidence that the coin is unfair, even though we didn't get exactly 50%. There's roughly a 10% chance of getting a result this extreme, 217 out of 400, or more extreme. In other words, 54% getting a result more extreme than 54% in the sample of 400 coin tosses, heads. Basically, it's just that could happen with reasonable probability. We don't reject the null hypothesis. Final example. Okay, so let P be the fraction of late flights on an airline after they change the boarding process. In other words, they've tried to change the boarding process to make the fraction of flights late be less. And there's a lot of scientific studies on what's the best way to board an aircraft. You can look that up on the internet if you want to. So the null hypothesis would be basically that the fraction of late flights is going to be bad and we haven't improved it. So that the fraction of late flights will be greater or equal to 30%. Let's assume the status quo was we had 30% late flights. The alternative hypothesis would be after changing the boarding process, the chance of a late flight is less than 30%. And let's let alpha be 0.01. And what data do we have? Suppose we tried this new boarding process on 300 flights and 50 were late. Now that's 17%. That's a lot less than 30%. Is that enough to prove that we have a significantly better boarding process? Well, the hypothesis test will tell us. So we put in the P0 here should be 30%. And basically, when we get 50 successes out of 300, we put that in here. And now you look at this. This is a left-tail test, and the probability or p-value is like 8 in 100 million. Okay, that's way less than 0.01. So we are quite sure that basically the new boarding system is better than the old boarding system. Now, if I put something like an 89 in there, which is 29% or so, okay, see, the p-value would be near 0.5. We really wouldn't have any proof that the boarding system we changed to was better with that 89 out of 300. Okay, even though 89 out of 300 is less than 30%, it's very close to 30%, we just wouldn't have much proof. So I think in summary, all you have to do here is put in the null hypothesis, put in the number of successes, the number of trials, figure out it's a left-tail test, right-tail test, or a two-tail test, compare your p-value from the spreadsheet. You don't have to type these formulas in again, to the hypothesized value of alpha, and if the p-value is less than or equal to alpha, reject the null hypothesis, otherwise accept the null hypothesis. Now in our next video, we'll talk about testing hypotheses concerning equality of variances.